using feet instead of meters. Some were using meters, some were using feet, and they lost a Mars orbiter that cost $125 million. So these are the kind of reasons why we insist on you guys being able to convert units and understand units and always provide us units. So when you give us a graph, when you give us anything you report on. So unit change, the dimension don't change. So the dimension of time are always dimension of time, and velocity is always length per time. We'll be talking about mass, we'll be talking about length, time, number. And numbers are useful. For example, for number we use moles. You'll use that in chemistry a lot. And units provide us the actual yardstick we're going to use to describe the quantity. It can be pound, it can be gram, it can be kilogram. These are different yardsticks that we use as our basic unit, but they all relate to the same dimension. Coordinate system, again, we usually use Cartesian ones, which we describe if it's a position of something moving in space. We'll provide 3 coordinates in space plus time when it was there, and then we can do distances by simple difference of the position. As so, and then we'll describe also things like vectors. You've learned it in physics. Velocity, it has 3 axes. Or position has 3, so it's 3 number. It's just a way to describe something that has more than, it has a direction and not just a size. Scalars describe the size. So when I talk about speed, it's a scalar. When I talk about velocity, it's a vector. It has a direction. These are simple things you're learning. Some of you are learning right now when you're taking physics in parallel. Some of you had it last year or the previous semester. Measurements, as we said, always have an uncertainty, and it might depend on the measuring device. My device is not tremendously accurate. My scale is good to within a gram or or tenth of a gram or a hundredth of a gram. I cannot do any better with that scale. This is to start. But there's also another, this is just one source of the uncertainty. The other might be that my scale has not been calibrated. It's off by 3 grams. And I think that if I only took the precision as the source of uncertainty, I would say, oh, I know it within a tenth of a gram. But I might actually be off by 3 because I'm far away from the true value. So just another description of it is very nicely provided here. So this is not accurate and not precise. I have a shotgun of a target where I shot both off the center and they're far away from each other. But this is much more dangerous than this one, because here I get measurements that are repeatable. So I have a strong sense that I'm getting very good measurements. But no, I'm off. I'm quite off from the center. This is your ideal situation. You want to be accurate and precise. But this is not so bad. Being accurate and not precise, I can still get a good estimate of where the center is by shooting more. It turns out that when you take independent measurement of the same quantity again and again, you will end up, you can estimate the position of the right position of the average, for example, better. It goes like the accuracy is reduced like the square root of your number of observation. So by shooting more or observing more of the same quantity, I'm going to get closer and closer to the center, which I cannot do here because, again, I'm going to get a wrong sense of where the center should be or where my mean is. So that's an important concept. That's important for you to know. So whatever measurements you do, you always need to know about it. It's basic statistics. There's 2 kinds of statistics that you've seen in the past. One is called parametric. Parametric is when I know something about the underlying distribution. If I think it's normally distributed, the average is right there in the middle of all my measurements, and I know something what the standard deviation describes in terms of the distribution. But I don't necessarily know what the underlying distribution is. So it's often much more reasonable to talk about non-parametric statistics, talk about the median, talk about the percentile, 75 percentile. 75% of the observation are below, 25 are above. Here you don't assume anything about the underlying distribution. You simply describe how data is distributed. What's your mean, what's your max. This is, in this case, you don't have to assume anything about your underlying distribution. That's why it's more robust. If you talk about the median, you know half the observation are above, half the observation are below. If you talk about an average, you don't know it unless it is a certain distribution, which is one that has it. So here is an example. These distribution, and they're synthetic, I made them. They're supposed to be a potential distribution for the size of an adult Atlantic salmon. And they both have the same average. But you can tell immediately that they look, this one has the majority of the observation of the fish caught are 10 centimeter. Here they're about 21 centimeters. So they're very different distribution. They have exactly the same average. So qualifying them just with the average is not sufficient to tell you what it is we caught. If you know something about how, where the median is, you might, so in this case, the median is at 15 centimeter. In this case, it's in 21. The distribution around that, here it goes from about 5 to 40. Here we go from 15 to 28. So it's very different, even though they have exactly the same average. So average don't suffice, and knowing something about how things are distributed is useful. Now we're going to talk a little bit about the difference between solids and fluids. Self-supporting solids. So any solid you have supports itself. You have this table, it supports itself, even though on geological time it might eventually collapse. But on the time scale we care about, windows are still solid and they support themselves. But liquids do not, so you have to put it in a container. That's what's going to support it. A gas actually fills the whole room. Air here fills the whole room, and including the water vapors in it. But if I put it in a container, if it's a liquid like water, it does not fill the whole room. It's staying within the container. So that's what will separate gases and liquids, which both are fluids. We consider both of them fluids. They both flow, and we'll talk about that in a second. So solid, in terms of the stress applied on them, if I push, I apply stress. Stress is a force per unit area. If I apply a stress on it, the deformation, this deformation, is proportional to the stress. This deformation sideways, one side or the other. However, in a fluid, what happens, if I do that, the fluid is going to start flowing. And so the rate of that is proportional to the stress, the rate of deformation, not the deformation itself. It doesn't come back to where it was like a solid would. It keeps flowing in the direction the stress is applied. Stress you can think of as wind blowing on the ocean. That would be an example. Here is an example of what we call a non-Newtonian fluid. So it's a fluid that behaves somewhat like a solid, some like a fluid. It's a great funny movie. And I'm going to just jump over some section in it. So you have these people, and you probably played with oobleck when you were kids. So it's made of starch and water. We can close the door over there. And I can increase the, it's in Spanish, so we cannot, I mean, having sound is good, but it's not going to help a lot. So obviously they can run on this thing. When you put a strong pressure on it, it supports your weight. But now I'm going to move it about a minute later, and we're going to have the guy in white go over it. So those of you who understand can tell me what he says, but so now it's behaving like a liquid. Once you stop applying force on it, it behaves very differently. Okay, so these are special fluids. They're not the fluids we're going to talk about. It's just to show you that not all fluids behave the same. Some fluids behave in ways that are fascinating, but are not the topic of this class. Okay, so we'll talk to you now about the continuum hypothesis. When we talk about a fluid, we don't describe the motion of every individual molecule. We don't have to, even though one would think that, from statistical mechanics you want to. We treat the fluid as a continuous medium, disregarding the molecular nature. And it turns out We can predict a lot of behaviors doing that. We don't have to go to the molecular level. It's too hard. We're going to have to deal with 10 to the 23 molecules and how they move in a small. So this is a great hypothesis in terms that it allows us to describe a lot of things that happen with fluids, including right equation for their motion without needing to go to their molecular level. And then certain molecular properties, like the motion of individual molecules, have a macro expression like temperature. Temperature is a result of their vibration. Viscosity relates, again, to their vibration and the way they interact with each other. So that's a very important assumption about fluids that seems to work extremely well in describing how they behave. And so, as I said, some physical properties do have their origin in molecular nature of fluid. Density is one of them, temperature and viscosity. We can relate to that. And the last thing I want to talk to you about is the fact it's what we call the no-slip condition. And the no-slip condition is very, very important. And we'll come back to it a lot in the class. It's this notion that a fluid next to a surface move at the same velocity of the surface. So if you're a fish, the fluid right next to the fish moves with the fish. If you flow over a bottom, the fluid right next to the bottom doesn't move if the bottom doesn't move. That's very, very important. So here I'll show it to you. It doesn't matter what the viscosity of the fluid is. It's the same for wind just as much as it is for... So here is fluid released right next to the bottom, and then they're going to take this pipe and take it up. And you can see the dye right on the bottom always stays here. It doesn't flow, even though the current is in this direction. See, now they can erase it or scrape it off, but let's see it again. Let's see. That has phenomenal implications on behavior. It also means that whenever you swim in water, you have to spend energy dragging that fluid with you. This is what we call drag on an object that goes in water. Okay? Where am I? Another property, I talked to you about stress being force per area. These are associated with the strain. So the strain is the displacement we're talking about. So if I go in this direction, this is the strain associated with the normal stress. Normal stress is what we call pressure. And shear stresses sideways, are also associated with motion, and that's what we call the strain. It's just for you to understand what the concept that you might see in papers or might see in engineering literature. So to summarize what we learned today, we need to study physics to better understand the biology of marine organisms. And this is not the only reason. I'm a physicist. I study physics for its own purposes or for resuspension of sediments and other things. But since most of you are marine biology major, it's crucial for you guys to know about it too. Need to keep track of units, because if we don't, we may make big and costly mistake. We need to keep track of uncertainties in physical measurement because we don't know anything exactly. And this tells us how well we know something, and that might be important for whatever application we use it for. It is very convenient to treat liquids as a continuous medium. And it turns out it works well without having to account for holes between molecules. And liquids differ from solid and gases in some fundamental ways. And we'll mostly be preoccupied with liquids. We'll also have some labs that involve gases, because gases are important when you dive, for dive physics and things like that. So we'll mention gases as well in this class. Any questions? So I'll see you in the lab. It's going to be fun. The lab is tremendous fun, and there are only 12 of you in each one. It's going to be a lot of playing together. And those of you who've changed, I'm going to give your names to Jody. If you have the time and you can do it, you can talk to Jody as well. Great. If not, she will reassign you to the third lab session.